Alright, so what we want to prove here is that f being differentiable at a point is equivalent to all of its component functions being equivalent at that point, and then we can write the derivative in this form. So this makes sense because the derivative is going to be a linear function from r to r2, and so if you take something in r, then wait a minute. Yes, because if you take an element in, if you take a real number, you think of that as a 1 by 1 matrix. And so if you multiply on the left by this 2 by 1 matrix, then you end up with a 2 by 1 matrix. And so this does indeed map R into R2. Okay, and this is a neat exercise because it turns out that not only is this true, but it's true more generally. And we will sort of see, like, this doesn't just hold for f from r to r2, you could increase it to rn. And essentially, the same proof that I'm about to give will hold. And furthermore, you can generalize it even more if instead of the domain of f being r, if it's rm. And we will see that in the next section. But it's also kind of nice because understanding simpler theorems, or like understanding a particular case of a theorem, can help understand the more general theorem. So anyways, I sort of like that, giving a very simple case of a future theorem as an exercise before getting to that theorem. Anyways, so let's suppose... So first we're going to do the backwards direction. So suppose f1 and f2. I'm going to use subscripts because I don't like using superscripts unless I have to, because it can be mistaken for exponents. Suppose these two functions are differentiable at a. We want to prove that f is differentiable at a and that f prime of a is given by this matrix. Then we know that 0 is the limit as h goes to 0 of f1 of a plus h minus f1a minus h times f1 prime of a over h. Because this is the derivative definition. And of course these absolute value signs, they don't really matter in the one-dimensional case. You can take them or leave them, but in the two-dimensional case you have to have, or in the multi-dimensional case you have to have them, because in general the thing on the top and the thing on the bottom will live in different vector spaces. Alright, and so we also have this equality for f2. So we'll just write out everything again. f2 prime over h. Okay. So let's take the limit as h goes to 0 of, now we're going to do f of a plus h. So this is not f1 or f2, this is f itself, minus f of a minus h times f1 prime of a. This is also nice because if we use subscripts, we don't need the extra parentheses. So let's see here. This, we need to take the transpose just because of how it's defined. We're dividing by the norm of h. I'm going to have to continue this on the next line. So this is the limit as h goes to 0. So this looks like f1 at a plus h, b plus h. No. So by definition, f of a plus, why did I add b? This should be h. F of a plus h by definition is f1 of a plus h, f2 of a plus h. And of course, this vector needs to be transposed, minus f1 of a, f2 of a, transpose. And then we keep this thing. So we can bring this h to the inside if we want. Doesn't really matter. Transpose. And then we still divide by the norm of h. And now if we add these vectors together, we get f1 of a plus h. We just combine all the things in the first coordinate minus f1 of a minus h f1 prime of a. That's the first coordinate, and then the second coordinate is going to be all of the things for f2 prime of a. We're still taking the transpose and dividing by the norm of h. And now we're just going to use the triangle inequality because, okay, well, I'll do it and then I'll explain it if necessary. So this is less than or equal to the limit of f1a plus h minus f1a minus h f1 prime of a over h. And then we take that entire thing and we add. So this plus, it's, I guess if you're going by like the whole like PEMDAS thing, like this doesn't make sense. But I'm assuming that as a reader you're intelligent and can see that like I'm clearly like this thing divided by h, so that's its own separate term. And so then we're adding here. Actually, this might work with the order of operations. But basically the norm of h is the only thing in the denominator there. Sometimes it's easier to write things that disobey the order of operations, but you can see from the way that's written what is intended. That's why, like, if you see on all those like Facebook posts are just like, what is this thing? And it's just like an order of operations question. There's a really good VHart video about it I think it's like an end section of one of her videos where she kind of explains that that's not, well, it's really not a math problem. It's just a matter of, it's like a very poorly phrased sentence and an ambiguously phrased sentence. It's not like a math problem. It's just trying to trick you with ambiguous writing. So really all that's happening is that there's poor writing. But anyways, tangent over, we got this thing. It looks just like this. And here, we have this. And then this, all of these things are 0. And that is because, and this is, so where the inequality holds, because for all, if we take any x and y and r, then x squared plus y squared equals norm of x squared plus norm of y squared, which is less than or equal to the norm of x squared plus 2 times the norm of xy plus the norm of y squared, because we've just added this term 2 times the norm of xy, which can only possibly be positive. But then this is just the norm of x plus the norm of y squared. So we take square roots and get x squared plus y squared is less than or equal to norm of x plus the norm of y. So really the way that we can think about this is that if x and y are the coordinates of a vector, then the norm of the vector is less than or equal to the sum of the absolute values of the individual entries. And so that's all that we did in this inequality. We took a two-dimensional vector and we said that it was less than or equal. We took the numerator here and we said it was less than or equal to the absolute value of the first coordinate plus the absolute value of the second coordinate. Then we broke it up into two sums, and then we took the limit and we got 0, precisely because f1 and f2 are differentiable at a. So by definition, these limits are 0. So f is differentiable at a, and furthermore, f prime of a equals f1 prime of a, f2 prime of a transpose. Alright, so conversely, suppose f is differentiable at a. So this means that there must be some lambda 1 which depends on a and a lambda 2 which depends on a, such that f prime of a, well, this is a linear function, so we have to define it. It's a linear function from r to r2, so we need to have an input x. And this, by definition, will be lambda 1a x, lambda 2a x transpose. So then we can do another computation. So basically here we just send, it's very similar to what we did before, but we do like a triangle inequality thing. So this is the limit as h goes to 0 of f of a plus h minus f of a minus, then we have lambda 1 of a times h and lambda 2 of a times h. This thing is being transposed. We're dividing by the norm of h. Then we can take this thing and we can take f of a plus h and f of a, write those as a vector f1 comma f2, and then again when we subtract these vectors we can write it component wise, so we get f1 of a plus h minus f1 of a minus lambda 1 of a h, and then we have f2 of a plus h minus f2 of a minus lambda 2a of h. This whole thing is being transposed. We're still dividing by the norm of h. And so this thing in the top, we've got the norm of a vector, and that's going to be greater than or equal to the absolute value of any particular entry, because the square root of x squared plus y squared, well, x squared and y squared are both positive numbers. So if you remove one of them, then you've only increased, or you've only possibly decreased what you have. So the square root of x squared plus y squared is greater than or equal to the square root of x squared, and then that just is the absolute value of x. And so this is the limit as h goes to 0 of, and we'll just say fi of a plus h, because this will hold for both f1 and f2, minus lambda I a of h over the norm of h. And this holds for I, which could be either 1 or 2. No, I forgot the greater than or equal to. The inequality above must be equality. Oh, did I mention that for the first part? I don't think I did. Okay, so obviously we have this, so just going back to the first part, this limit of f of a plus h minus f of a minus h times this blah blah blah, this whole limit here, we prove that this is less than or equal to 0. However, the limit must be greater than or equal to 0 because it's a limit of a norm of something. And the norm of something is always positive, so it's a limit of positive numbers, so it must be greater than or equal to 0. Thus, this limit is both greater than or equal to 0 and less than or equal to 0, which implies that it is precisely 0. Okay, so having gotten that out of the way, let's return to this. The greater than or equal to above must be equality, because we've proven that this limit here, for this particular I, is less than or equal to 0, but it's a limit of positive terms, so it must be greater than or equal to 0. Thus, it is precisely 0. So the inequality above must be equality. And so, by definition, f is, or fi is differentiable at a. And we have a formula for fi prime of a. Well, as we can see above here, it's just lambda I of a. Because if we take fi prime of a and plug in h, we get lambda I of a times h. And so this implies, furthermore, that f prime of a is in fact equal to f1. Well, we know already that it's equal to lambda 1 of a, lambda 2 of a, but we now know that this is equal to f1 prime of a, f2 prime of a. Okay, and that's what we needed to do for this exercise, and so we are done. And in the next section, we will generalize this to differentiable functions from Rm to Rn.